talk already. Again, the second disclaimer is that I gave this talk already several times. So if you heard it over the last whatever 12 or 10 months, it's going to be about the same, maybe just a few little tweaks. So yeah. Just again, just a little bit of a disclaimer. And we also I wrote a paper about it in case you're interested for International Hydraulic Fracturing Technology Conference. It was in Amman in September 2025. So it's all has been published, and so it's all available. So again, if you want to go and learn a little bit more about it, or you miss something, it's available in the paper. And so this is something I've been working on the last few years. Maybe again, I was presenting for the last year, and then maybe I was working for another year before that. It's about horizontal hydraulic fracturing. I mean, and it's something which is it's really fascinating, right? I mean, if you think about it, because we all learn over the years that hydraulic fractures must be vertical, right? I mean, so we indirectly assume, or in most cases, that they're vertical, but they're not. This is not always the case, right? And so I hope I'll convince you that I mean, I'm talking about shales, by the way. I mean, of course, if you know, there are other applications for which it could be horizontal, but for shales, we typically think that fractures are always vertical, but that's I mean, hopefully I'll convince you that this is not always the case. So first, just a little bit of again, just make sure we're on the same page. So here on the top, sorry, on the left, I plot stress versus depth qualitatively, right? So we have the minimum horizontal stress and vertical stress. And so typically at large depths, you know, more than about 2,000 feet. Again, if you like SI units, multiply by 0.3, so it's 600 meters, like give or take. So the vertical stress exceeds minimum horizontal stress by some margin, and because hydraulic fractures are lazy, right? I mean, all physical systems want to minimize, the work or energy. So they actually open against the minimum principal stress or the least principal stress, which, at larger depths typically is minimum horizontal stress. And at shallow depths, for minor energy storage applications, we often have the opposite happening. And so that's why we see a horizontal or some horizontal fractures. But again, for petroleum and geothermal, we often assume that the fractures, hydraulic fractures, the induced hydraulic fractures are vertical because we are at larger depths, maybe 10,000 feet, 7,000 feet kind of scale. And the question is it always true? And so the next few slides, I'm going to show you some field evidence that I was able to find, which is available to public. And again, when you see just one piece of evidence, you can argue with it. Maybe something was wrong. Maybe it was some unlikely event. But as soon as you start putting it together, start making a little bit more sense. I mean, you cannot ignore it. I think we reached the point that we cannot ignore it anymore. So that's what I'm trying to to say. So one of the first mentions of horizontal fractures, it was during water flooding in California. It was done by nobody by Chris Wright here, the first author, who is in DOE right now. And so they used tiltmeters. So it was again water flooding operations in California. They used tiltmeters at the surface, and so the tiltmeters, they can they measure the inclination angle of a surface is in like with very, very high precision, like nanoradians, right? And so again, so you inject water on the ground, so you have deformation of the surface, and you measure it. And that's kind of the signals that they observe sometimes. Again, it's screenshot from the publication, so it's clear indication that again this is like top view, right? And so it's very, very symmetrical. So this is an indication of horizontal fracture. Because again, the vertical fracture would be kind of it would be oriented, right? It would have kind of a directional input into it. And so they analyze this data, and so that they interpret it in so-called volume of horizontal fracture component. I don't know if you can see it. This is horizontal axis here. And so in the operations again in California, so this depth, by the way, 2,000 to 3,000 feet. So it's not very deep. It's conventional. But sometimes they had 100% of horizontal fracture components. Sometimes they had some of it, right? And so this is one of the first indications that or observations in the field of horizontal fractures. And again, you can argue with it. Obviously, I mean, you can say, hey, what if it is for elastic effect, right? So I mean, basically, you have all fluid diffusion around fracture. It's very strong, high permeability. But nevertheless, again, this is the first mention in the literature that this was happening. The second one I want to cover is observation in Marcellus. This is by Alali and Zobak. 2022, fairly recently. So again, Marcellus has fairly high stress regime. So this is a stress map, again from Zobak. And this is, so here we can see we are in a strike slip regime, meaning that the maximum horizontal stress is a maximum stress overall, and then intermediate stress is vertical, and the least principal stress is SH mean. But the difference between SV and SH mean is kind of fairly small, right? And so what these authors reported is microseismic evidence of horizontal fractures, essentially. So that's what we see here on the screen. This is side view on the wells, and on the top we see microseismic cloud. In the middle we see the well trajectory as it goes from one formation to another. And then, as you can clearly see, that as soon as we are kind of in the upper formation, we do record some height growth in microseismic. And as soon as we land a little bit deeper, now it's all completely flat, so almost no height growth. And this distance is, so the scale is from say -50 to -250, so it's 200 feet. So one scale is 200 feet. So this indicates that your height is maybe 100 feet, at least. But again, authors interpret that this is horizontal, so that we have purely horizontal hydraulic fractures. And to further kind of confirm this, the authors plot these ISIPs. So these red dots, this instantaneous shut-in pressure, what they measure, or red markers, right, as you can see here. And this is the numbers I think it's probably going to be MPa. And the dashed black line shows the estimate of vertical stress. So as you can see, is when we have basically high growth, our ISIPs is below vertical stress. And once we see no high growth, ISIPs are above vertical stress. And so again, the interpretation, again, on average, I have plus minus here. But the interpretations here is that, again, we have very high pressures, shut-in pressures, and we have no reported high or observed high growth. And so basically, we think that this is indication of horizontal fractures, or purely horizontal fractures. And this, by the way, occurred in several wells. So it's not just one office. So again, I mean, you can argue maybe your, geophones were not good enough. No, it occurred in several wells. And so again, it's about the same picture. So in this case, now we land in a little bit lower formation, right? So this is lower Marcellus, here is green. So here we land a little bit lower. So before it was above, and we still have high growth through everything. But as soon as we land in here, lower Marcellus, now it's all horizontal. And again, ISIPs climb up. Again, this is my favorite example because you cannot argue with this, because with microseismic, you can argue that, it's this data is subject to interpretation, right? Tiltmeter is, subject to interpretation, right? So what if your algorithm is incorrect? You have, bug in the code or anything. With this one, it's kind of hard to argue because that's what happened. So when I worked before at Van Gonten Labs about 8 years ago or something like this, so we had a project in Eagle Ford, right? So one of the clients had a pad here. This is side view and this is top view, and they recorded microseismic. And again, you can see very nice high growth. You can have orientation. I mean, again, all of the stages kind of consistent with stresses. So everything is nice. But then they drilled a vertical core outside a microseismic cloud, so that because they were planning to do another pad here, I think. So basically, they drilled a core for analysis, to measure properties, permeabilities, layers, so, all this stuff. And what they observed is propped horizontal fracture. It's kind of like a doublet here. I'm going to show a picture on the next slide. So this doublet is propped horizontal fracture. So it's, again, think about it. So again, it was about 2015. So again, so still fluid intensities probably were not as high. And then outside of microseismic cloud, and then we have propped horizontal fracture. So if proppant got here, then hydraulic horizontal fracture probably would have been somewhere here, probably double the size, right? So it's going to be somewhere here. So that's large scale. So again, so all I want to say that this is large scale feature. So it's not something that occurred near the wellbore as part of near wellbore complexity. It's large scale feature that propagates kind of far away from the well, or can propagate. I'm not saying it propagates. I'm not saying that horizontal fractures occur on every pad, on every well, on every treatment. No, occasionally they can occur, and this is a field evidence that clearly shows it. So again, this is a picture of the actual core. And again, and this is, by the way, of all courtesy of unconventional engineering, because at the time when they had it, I mean, again, for those who work in industry, you know how it is. I mean, you have a project. I mean, you have to model it as all vertical fractures. You model it, you optimize it, and then you move on. And luckily, I was able to, request this data and receive the permission to use it and share it, because I think it's very, very nice piece of evidence that we can use. And now, all these pictures are also published in the publication that I mentioned. So again, with all the permissions. So again, we as a community, we have it, which is great. We can reference it. But that's how it looks like. Again, there is no other way how you can get propagate in this vertical core. So that's what it is. And also, interestingly, it occurred in Eagleford. And if you look at the stress map here again, it's normal faulting. I mean, it's normal faulting, which means that vertical stress is the largest principal stress, and yet we're able to open up the bedding plane and prop it. Just think about it, right? So that, because some people think that, hey, I mean, you may have these horizontal fractures only if you are in strike strip or reverse faulting, kind of close to these two, but no, it's normal faulting. So that's life. Let me show you another kind of indirect evidence for large scale horizontal fractures. So this is a review of casing deformation data, up to 2022, against outdated, but you can see how it kind of grows exponentially. And again, I really like this publication. Again, if you want to get up to speed in casing deformation, from field perspective, I mean that's the one to read. It has all the statistics, but there are distribution by country, and there are also different types of casing deformation. What I want to emphasize is this BPS. It's called bedding plane slip. And so there are a lot of them in China, in Canada. It's not 100%, it's 20%, 37, but it's not negligible. And so this bedding plane slip basically is when you stimulate your reservoir, you hit this bedding interface, and then it slides, and now your vertical section of the well sees something like that. And again, if it's vertical section of well sees something like that, I mean, you cannot, pump any tools through it. And so basically your whole well, sometimes the whole pad has some issues. I mean, there are ways around it, they can drill through it, they can straighten it, but, it's extra operational costs. Okay. But to me, this bedding plane slip is something that can be associated potentially with horizontal, subhorizontal fractures, right? Because again, if you open the fracture, now it cannot sustain any shear if you open a horizontal fracture. Now, if it's not perfect horizontal, now you can have some shear component on it, and now it can slide and have this and cause these issues in the wells. And again, this has been reported in many places. I have two more for you to digest, because I mean, as I said at the beginning, if you have one or two, you can argue. But now, if I show you 10, in this case, again, I mean, at least you'll agree with at least some of them, because some people like microseismic, some people like core, some people like fiber optics. But so again, if you in fiber optics and you trust it, well, this is for you, right? So this was a paper presented back in 2024 at HFTC in Woodlands. And I think we had an ARMA seminar on it, maybe at about the same time, maybe plus minus, a few months. This was situation-based in China, and so they had a horizontal monitoring well, and they were observing signals kind of looking like this. Again, this is modeling. I'm going to show you the actual signals on the next page. But then interpretation is that we have sub-horizontal, so it's a little bit inclined, bedding plane, which has to have both tensile and shear component. So if you have tensile component, that's kind of the signal you would see on monitoring well. And again, for those who don't know this, fiber optics, they essentially measure stretch along this well, basically stretch, right? So and so all these figures, this is your measured depth, so basically the distance along horizontal wells, so this x-axis, and this versus time, right? So what we see is how kind of this semicircular feature kind of hits this monitoring well, and then it increases in size. But long story short is that, again, if you have tensile only, signal is symmetric. If you have shear only, this signal is completely asymmetric. But when you have both tensile and shear, you kind of signal kind of mixed mode. And here on the left is how the actual signal look like in the field, and it was consistent among several stages. And this is on the right is modeling interpretation. And again, interpretation here is that here we have two vertical fracs, and then kind of like a halo or sub-horizontal fracture above or below them. And so they both do, opening and shear basically. Pretty complex, but again, it's I want to emphasize this large scale, right? So this is 1,000 meters here, and so there's going to be probably 100 meters, a few 100 meters. So this is not like your little simulation of interface. It's large scale observation. And by the way, here they also saw it for several stages, and they even saw when this horizontal plane crossed the monitor well. And again, so if you didn't catch, I mean, I think we had a presentation of this paper. I think it was recorded maybe a couple of years ago. The last one, which was presented just in February this year, and Professor Jean from School of Mines actually is going to give an extensive talk about it in July. He's scheduled to do so, but I'm going to just mention it briefly. Again, also fiber optics observation in Eagleford. Again, going back to Eagleford, where we had the propped core, normal stress regime. Again, we had treatment well and horizontal monitoring well, about 1,000 feet away. And here again, we're looking at measured depths versus time. On x-axis, you see these little stages, how they were pumping along the well. These rectangles is where we expect fractures to be, right? So again, it's a little bit messy signal, but again, we expect fractures to be here, given stress orientations. But early on in the well, it was all nice, and then as we kind of progress along the well, we expect fractures here, but instead we see this kind of thing further away. And again, and this should be familiar because this looks pretty much like this. And so essentially, so I gave this, I drew this little cartoon. So you have treatment well, monitoring well, you expect your vertical fractures to hit along this, SH max direction, but instead you kind of have, an offset, large scale horizontal or sub-horizontal fracture shearing, and it has, kind of a few thousand feet offset because again, you expect it here, this 1,000 feet here, so maybe about 1,000, 2,000 feet offset here. So in reality, you have something like this. So that's how we can interpret this observation. Finally, again, this is all about field observations, and so I just just a little bit of disclaimer, because I mean, people were just researching and investigating this bending plane interface for a while now, and they studied from various angles. Like this publication here, right? So you can have a kind of local shear here, and now you can have like a pinch point, or you can have T-shaped fracts here, or you can have step overs, or this numerical simulation, right? So again, so you can see have a lot of stimulation of this bending interface. But I just want to say that for me, this is all looks like stimulation of interfaces. So basically, kind of your local. So you have your local deformation or local features to mostly vertical fractures. So again, so majority of fractures are still vertical, but these are kind of fairly local features. And to me, horizontal fractures is something that propagates at large scale. So something that is at least comparable or larger than the vertical fractures. And so to me, this is a difference. And again, previously people focusing mostly about this one and not kind of large scale horizontal fractures. So that's, again, it's a little bit of a distinction. So this is summary field observations before we proceed further. Again, I hope it convince you that we may have occasionally horizontal fractures. And again, they were observed using tiltmeters, microseismic, core, and fiber optics, and also casing deformation. And so that's quite a lot of field evidence, right? And again, it does probably not happening in every pad and every well, but it occurs in nature. Let me put it this way. And these are large scale features, thousands of feet or hundreds of meters, maybe 3, 4, 500, hundreds of meters. And so yeah, now let's look at the rock, right? Let's try to discuss a little bit of why do we think we see those in shales? Because again, as I said in the beginning, we don't expect it based on your stress conditions. At least, I mean, again, the ones that basically we don't expect them, right? So let's see. The first thing is I want to emphasize that shales are known to be viscous, and Mark Zobak is the one who was convincing us about it. And so he did lab experiments, and he basically plotted creep versus time on shale samples, and you can see you have some creep. For those who like mass or viscoelasticity, that's basically roughly how it looks like. You have a spring in a dashboard. But what does it mean? Physically, it means that at geologic timescales, these rocks essentially behave like liquids, right, or fluids, so that um, they have isotropic state of stress or nearly isotropic state of stress, okay? Or at least it's kind of like a limit towards nearly isotropic state of stress. It means that for shales, even though we define these stress regimes, normal and reverse and blah blah blah, these are kind of like average, right? So some sort of average, throughout the formation. But locally within shales, you can have very high stresses. And very high minimum horizontal stress, almost approaching vertical stress. And to prove this point, again, this is a screenshot from one of the publication from Zobak, as a defeat analysis, and they plotted fracture gradient in sandstones here in yellow markers, and fracture gradient in shales, and so they are all red. And these are different gradients, 0.8 psi per foot, 1 psi per foot. And vertical stress gradient is right about 1 psi per foot, maybe 1.1, 1.05, something like this. And so you can see again, so your average stress state could be normal faulting, right? But locally in shales, you may have very high stress relaxation rates, so that your SHPN is almost equal to vertical stress. Again, I almost saying almost because again it's all time dependent process, and now you have tectonic movement and blah blah blah. So this is not perfect, but it's kind of it's approaching it, I know, asymptotically. This is one part. And the second part of the story is tensile strength anisotropy. So if you ever look at the core in a conventional reservoir in shale, it looks something like this. So this scale, horizontally, is I think about 4 inches, to 10 centimeters, give or take, maybe a little less. And so vertically, again, it's maybe a little bit more than that. But when you see the scale, right? So you have very fine lamination on centimeter scale level. But it's not lamination that I want to actually emphasize, is you see these cracks, right? And their orientation, right? So these are the planes of weakness. So basically, as soon as you extract the core, you always shake it and so on, and so it breaks. But it always breaks along these planes of weakness. What it means that the tensile strength in vertical direction is much slower than in horizontal direction, right? So it's much easier to break it along the ledge. And sometimes you take this core in your hand and it basically breaks. So it's almost no effort. And so it's virtually almost zero tensile strength in the vertical direction of kind of this delamination strength. And this can also play a role, right? This can also play a role because it's much easier to initiate horizontal fracture kind of along this weak interface compared to vertical fracture. And to prove my points, this is a lab experiment from Ali Abdelaziz and Giovanni Grosselli from University of Toronto. So they did a large block test on Montney Shale. So again, this horizontal wellbore here in orange, and then we have the vertical stress 29 MPa. I don't know if you can see it. The max horizontal is 41 and minimum horizontal 23.6. So we expect to have vertical fractures, right, perpendicular to to the well, kind of transverse fractures, but instead we have all this, bedding plane action going on. And again, and the interpretation is that, again, this is all related to tensile strength. So very strong anisotropy in tensile strength can promote horizontal fractures, even if your minimum horizontal stress is the least principal stress. Okay, so it's not just the stress ratio or stress anisotropy, but also tensile strength anisotropy that plays a role. And also, I hear stories from those people who did lab experiments that occasionally they also observe such results, but they never publish them because, again, our mental state is such that we must have vertical fractures. And so they basically threw these results away, and then they increased stress anisotropy until they got vertical fractures because for publications, they must have vertical fractures. You know what I mean? So that's, that's something that we need to, avoid. Because I think it's a very useful piece of evidence. And so just to sum up the rock features here is that, again, so shales, in contrast to sandstones, they have higher stresses, right? So high minimum stresses. And they're very laminated and so have very small vertical tensile strengths. And so basically this brings us to the point where it's much easier to initiate. It's not easier. Yeah, it's basically the the probability of initiating horizontal fracture increases, right? Because again, like in sandstone, you don't have tensile strength, or much of tensile strength and anisotropy. You have strong stress contrast, so there's pretty much no way how you can have horizontal fractures. But once you're in shales, suddenly now you realize, hey, now we are not that far. But that's not the full story, because operations also play a role. So the last bit of all this is operations. Because we used to have single fracture operations in conventional, and maybe in the early days it was single well. And now we have multi-well developments kind of like this. Sometimes 2 wells, 4 wells, sometimes it's really massive, like 50 wells, 60 wells, and they all being, stimulated, not at the same time, but it's kind of, it's very small time delay between them. And this obviously plays a role, right? And so I promised at the beginning of the talk to Anthony Pierce, I'm going to show some equations. So here they are. So let me give you just back of the envelope estimations of how to estimate the overall stress change caused by operations, right? So because again, you're starting with a situation in shales where the difference between minimum horizontal and vertical stress is kind of small. And now as you keep pumping, you kind of make it smaller and smaller and smaller until a tipping point when once you start having horizontal fractures, and until a point when the SH min and SV are the same. So that's the story. But let's go through the mass a little bit. So if you take a rectangular or PKN or constant height fracture, whatever you want to call it, with given volume, given area, given height, given elastic modulus, this is plane strain elastic modulus E prime. So then we have an analytical expression for the net pressure, right? And that's how stresses look like again against vertical fracture. So we have, this is your cross section SV and SH. That's how stress shadow looks like. And this is how vertical stress change looks like. And then if you plot them along the x-axis perpendicular, kind of like along the well, so see you have SH min stress, again, it decays with distance. SV is positive and then negative, and then SH max is kind of like this, basically just due to Poisson effect, is basically you multiply, you take, SH min plus SV and multiply by Poisson ratio. This is analytical expressions. But now, what if you start putting all these fractures closely spaced, right? As we do in the field, closely spaced. By closely spaced, basically, I mean that spacing is about 15, 20 feet, right? 25 maybe, and the fracture height could be 200, 300 feet, right? Could be more, right? But closely spaced basically means the spacing much less than fracture height. And so what happens is that your ISIP, or instantaneous shut-in pressure, or stress shadow, or it's kind of this measure of stress shadow, will start growing up, because as you have more and more fractures, now you start feeling these fractures, it's neighbor, and then second neighbor, and third neighbor, and fourth neighbor. But then at some point, stress shadow decays with distance, right? At some point, you kind of stop feeling them, and that's when you reach this plateau. And what I'm trying to do is trying to estimate what's this maximum stress growth. And because we're closely spaced, essentially, so we replace this spacing, essentially delta X, with a differential, and we go from volume to fluid loading. So fluid loading is your volume of fluid you pump per foot, or per length of lateral. It's cubes per meter, or in SI units, or barrels per foot in field units. And if you go if you substitute it in here, essentially what we need to do is we need to calculate this integral, right? So whatever these expressions we had, basically we can integrate analytically, and that's what we have. So the cumulative stress shadow, and again, we assume no leak off in this case, right? Or it's a very small leak off, at these distances, and which is reasonable assumption, because shales are not that permeable. But essentially, that's the main equation, right? So our stress shadow build is proportional to Young's modulus, which we know pretty well. Fluid loading, which we control very well, is one of these most important operational parameters, and people keep increasing fluid loading, and divided by fracture area, which we don't know very well, but again, we have some hints, based on microseismic, or based on fiber optics, or what it can be. But if you run the numbers, this increase is about 1,000 psi. And I think this is about like few MPa, right? I forgot. Conversion is probably 7 MPa, right? 7 MPa like this. And then the vertical stress shadow is 0 because again it has positive and negative, so the areas exactly cancel out. And then the SH max also increases, but just due to Poisson effect. So again, if you put Poisson coefficient as 0.25, then it's going to be quarter of this. But I'm trying to say that this is not negligible amount, right? So again, you start with very little contrast between SH min and SV, and now you keep adding gradually the minimum horizontal stress. And again, at some point you can reach a tipping point, and that's when your fractures can turn horizontal. And also, again, if you don't believe this estimate, right? So I mean, I ran a simulation in our software. Again, several stages. Again, these are not exactly constant height fractures. You see some are longer, some are shorter. But these black bars, again, it's hard to see the scale, but these black bars is where the estimate lands. And so it's kind of orange, right? And again, you can see that your maximums through shadow here is kind of like oranges. So it's give or take is roughly okay, right? Again, it's estimate. In for SH max, and again, it's also roughly orange radiation. So again, so we have it. And for the vertical, again, it's 0, but you cannot see the scale, but the scale is order of magnitude less than the scale here, and it goes negative and positive, right? So I mean, as we saw here, it's first positive and then negative. So it's very consistent with these analytical solutions. So again, so basically, don't take these estimates as exact and super precise. These are all just estimates. And my point here is that there are things that we do not control and things that we control. We don't control Young's modulus. We measure it very well, but we don't control it. But fluid loading is something that we control. And this could be a operational parameter which can reduce overall stress buildup and kind of reduce the likelihood of horizontal fractures. Yeah, so this summary of operations. So again, I promised some equations. So here they are. I mean, so the stress buildup in a single horizontal well is essentially, I mean, if you look at it, this is stress strain, this Hooke's law, right? So this is your stress, this is your modulus, and this is your strain. Because this is volume per length and per area. This is volume of injected fluid per volume of stimulated rock. So it's basically it's modulus times volumetric strain. That's it. I mean, and then there's a coefficient, on order of 1. But it makes sense. But my point here is that it's fluid loading that controls the amount of fluid we inject, controls how much stress we change in the formation. And so the more we change, the more and the more likelihood of horizontal fractures we will have, basically. And these stress buildup are not negligible. It could be 1,000 psi and maybe a few MPa, 7 MPa, like in this case, in this estimate, but it could be plus minus. And this is, by the way, this is for a single well. And once you start having more wells in a pad, kind of like a situation that maybe. No, I don't have it here. Like this situation, things get only worse because again, it's volume of fluid injected per volume of rock. And so, I mean, the more wells you have, the more fluid you inject, and so the bigger stress increase you'll have in the formation. Again, we can also make some estimates for that. A few words about modeling, and then I'll just wrap up with a couple examples, and we'll be good with questions. So just a few things. A few key takeaways is that now we need to worry. We have 2 more parameters. So one is the vertical tensile strength. So basically, how easy is it to initiate horizontal fracture? And so the initiation criterion is basically your fluid pressure exceeds total vertical stress plus vertical tensile strength, which is almost 0, right? Again, it's okay to, I guess, as a first approximation to use it 0. And this is an example. You can have, say, weak interface with 0 tensile strength, this particular depth, and so fluid pressure, exceeds vertical stress, and here you go, you start having horizontal fracture. Second parameter is, I call it debonding toughness, because we already have vertical toughness, horizontal fractures for vertical fractures, right? But for horizontal fractures, we are propagating along layers, right? So it's really, really weak. And so it's a new, we need to use a new value fracture toughness, which is very, very small. Because again, because the rock is very weak along these interfaces. So I call it debonding toughness, so delamination toughness. And again, we can use a fairly small number. But the reason I'm saying this is because, again, we typically don't think about these things, but again, we have strong anisotropy and toughness, tensile strengths because of these fine laminations. And ideally we need to measure all those new parameters in lab, but we can just basically take some small numbers and it's going to be good approximation. Another point I want to mention is that for vertical fractures, they hit layers, stress barriers, toughness barriers, whatever, and so the height growth is restricted. For horizontal fractures, for these interfaces, generally there are no barriers, right? So as soon as you have it, they actually tend to propagate far away. And again, they have almost no toughness, and so this actually amplifies, the distance or the scale of this horizontal fractures, because once you start propagating, you're just going. And we expect them to be mostly circular or radial, because again there are no barriers. Few examples, as I promised, and then I'll wrap up. So I tried to model situation in Marcellus, this microseismic observation. So basically, head inclined well, which goes through two formations. Again, I don't want to go through specific numbers, but I made a number such that essentially we have vertical fractures here, and then as you go a little bit below, you switch to horizontal, even though the vertical stress gradient I think 1.1, but the minimum is still lower, 0.95 in 105. So, and again, here you have horizontal fracture initiated from each perforation. And so that's why each fracture takes the same amount of fluid, and they all have kind of stress shadow between them, and they have all this kind of basically a lot of pancakes here, right? Again, and that's what have, potentially it looks similar as this interpretation of this microseismic signal on the right. Just a little bit more examples. A few more things I wanted to emphasize is that very often, if you have, say, multiple interfaces, like in this case, there is no limited entry between horizontal fractures, right? Because if you take a step back, how we promote simultaneous growth of vertical fractures, right? So we design limited entry so that each fracture takes the same amount of fluid. But here, these horizontal fractures, multiple of them, they're connected through fracture, which has fairly high conductivity. Against not as high as a well, but it's still fairly high when they open. And so what happens is that you can initiate a lot of horizontal fractures, but only one or two will grow large scale. So one or two will take all the fluid, as shown here and as shown here. And so again, this further promotes this kind of large scale behavior of fractures. So yes, you may have a bunch of interfaces, a lot of things, but it's probably one will eventually take most of the fluid and going to grow far away and cause issues. This is also a very nice example of taking deformation for those who have this issue, but it was a little bit of eye-opening. But once I explain it will all make sense. So here I have sub-horizontal pre-existing fracture essentially. So I had to make it a little bit of inclination so that I have some sliding. I have to have some mismatch of relative orientation of principal stresses. The difference between the minimum stress gradient and the minimum horizontal stress gradient is just 0.02 psi per foot between the top and the bottom. Okay, so this translates the absolute stress difference of 200 psi, right, or fraction of f of MPa, right? And so, on here on the left we see aperture, and this on the right sliding displacement, and then here again we see aperture and sliding displacement. And you see what happens is that with just a very small change of minimum stress, here we have very contained sliding displacement because there is no opening. You see, we don't open this Bayesian interface. Yes, we pressurize it, but and then pressure diffusion goes in, and then it causes failure. But it's very localized. It's all kind of limited by pressure diffusion in the fault, right? Yes, you can have high hydraulic conductivity of this fault or Bayesian plane. Now it will go further, but it's very limited. But as soon as you add just a little bit of pressure, now you are able to open it up to have this large scale aperture. And of course, as soon as you open it up, it cannot sustain any shear, and now it slides. But my point here, once you open it up, the hydraulic conductivity increases orders of magnitude all the time, orders of magnitude, even if you open up just 1 millimeter. And so suddenly now you can propagate much further. So here again, it's very localized, but once you have this horizontal, sub-horizontal fracture opening, now it can propagate much further. And because it cannot sustain any shear, you have the sliding displacement. And now if you hit the vertical section of the well, now you can start having these issues. Again, this is at least one mechanism of how can it be, because yes, you can have just pure sliding if you have very unstable situation, but if you have open horizontal fracture, you're almost guaranteed to have this problem. And the stress difference is very, very little. And why is this? Well, why is only 200 psi fraction of MPa? Because this is nothing else but the net pressure of a single fracture. Because what is the net pressure of a single fracture with almost no toughness? I mean, it's very, very little. And so it's again, and so this vertical fracture, so horizontal fracture doesn't feel the vertical fracture, doesn't feel the shadow from them. So it's a single fracture essentially in intact formation. And so you give it a few hundred psi, and now it opens and propagates almost forever because there are no barriers. So there is no like a warning light, you know what I mean? So you have no horizontal fracture, no horizontal fracture, and then suddenly you increase pressure just a little bit, and now suddenly you have potentially can have large scale horizontal fracture. So that's something to keep in mind. So just a few words about mitigation strategies. I know I'm running out of time, and then I'll wrap up. Um, the key message from this talk is that these horizontal fractures, they require both rock plus operations, right? So basically, so your rock has certain state of stress, certain strength anisotropy, and so basically, um, it will allow only certain fluid loadings, right, or operational, fluid intensities, has a certain limit. And so once you're gonna overstress the rock, so you pump too much, now you can potentially have horizontal fractures, right? And so the good news is that operations influence the result, at least in some situations, and so we have some control. And also, different locations are different, right? Because they have different rocks, different states of stress. So maybe in some locations it's okay to have these scenarios. Maybe in some, maybe it's not. And also, the most economical case would probably allow for some horizontal fractures. So I mean, I don't want to give this impression that as soon as you have horizontal fracture, that's the end of the world. Maybe we can optimize for just a little bit of horizontal fractures, just preclude very large scale horizontal fractures. So. Propagation deformation. So one thing that people can do, operators can do, is to reduce fluid loading, because again, maybe you skip a stage or two, or maybe you just pump less or at lower rate. And this generally reduces stress shadow, and so reduces the risk of casing deformation. So some operators just completely miss a few stages in the hill of the well, just in case. And also, you can produce some wells before fracturing neighboring wells. Again, you withdraw the fluid, so you reduce the state of stress. And then there are also things, I mean, mitigation strategies, kind of like this shown here on the bottom right. This is from CNPC, that they developed some special kind of mixture for the cement, which allows shear deformation kind of externally without deforming the casing. And some people just don't cement a vertical section of the well. So basically, it becomes liquid, and again, it kind of serves the same purpose. Well, I guess you have worse isolation, but I mean, you have less issues with deformations. So there are ways around it, but that's roughly what we know right now. So here's the summary. So again, the biggest thing, I hope I convince you that we occasionally have horizontal fracture, hydraulic fractures in shales, and this is a large scale, and they open. And again, sometimes they have propellant and the shear as well. And there's a variety of observations. And again, the main message is horizontal fractures is rock plus operations. So with operations, we control the total stress shadow that we generate in the rock. And so if rock has small capacity, then now you exceed the capacity, and now you start having horizontal fractures essentially. And well, I didn't discuss here that also horizontal fractures impact productions. They're not, I mean, first of all, you can have well-to-well interaction, kind of large scale. I mean, you have casing deformation, but also your vertical permeability is very limited. It's very small, right? And so you create this prop surface area or some surface area, along bedding interface, but it's not productive area. So generally, it's your injected volume wasted, and so in general, we don't want to have a lot of horizontal fractures. But as I said before, so maybe the most economic case will have some level of small scale horizontal fractures. So that's all I have. This is just my reserve slides. So thank you so much, and I'm looking forward to all your questions.
Thanks, Egor. Indeed, I think you've convinced us that horizontal fracturing can occur. That being said, there are some questions still.
I'm ready.
And the first is from Gong. And Gong is arguing that in many cases, in situ stresses become isotropic in shale. Will longitudinal fracturing be initiated first instead of transverse fracturing?
Well, yeah, this goes to near wellbore effects, right? So because you drill a horizontal wellbore, right? And so you can, have local state of stress kind of distortion due to this opening, in the rock, and you might have, longitudinal fracture there due to kind of this stress change. Because again, longitudinal fracture versus transverse fracture, they essentially see the same rock, rock properties or rock strengths, because they're both vertical. But they see a slightly different state of stress. So it all depends on local state of stress. But yes, this could be very true. You can have longitudinal fracture along the well. But to me, it's more like a small scale feature, which definitely affects the overall result, like connectivity between the fractures. But it's small scale because its size is proportional to the wellbore size, essentially. And so this is just a few inches here and there. But I don't expect longitudinal fractures on a scale of hundreds of feet.
Okay, the next question's from Ed Sieberts. Ed enjoyed your talk, and he's wondering how much frac width do you see in the simulated horizontal versus vertical fractures during propagation? And he's wondering whether you can get 100 mesh sand into it.
Yes. See, what happens is that in order to have a picture like this, as I'm showing this in your animation, you need to have nearly isotropic state of stress. You see, here we don't have a lot of previous stages and stress shadows. So for this specific example, so it was nearly isotropic state of stress. And if it's nearly isotropic, it means that whether you open, whether you have opening of vertical fracture, horizontal fracture, they face about the same closure stress. And so because they face about the same closure stress, plus minus, they have about the same aperture. So they're very, very comparable aperture. And so again, maybe a little bit less, right? But if you can fit, your sand in vertical fractures, like in this case, as soon as you open your horizontal fractures, you also fit your sand in horizontal fractures as well. So this controls a little bit. Oh, and I'll go back. So that's what you see, right? I think I wanted to say something else. Oh, another thing to keep in mind is that something that we don't have right now in simulations, but in reality we have, is that we have anisotropy in elastic properties, right? So, and typically the vertical Young's modulus, which horizontal fractures feel, is lower, maybe by 3, 4, or 5 times. And so essentially horizontal fractures propagate effectively in a softer rock. And a softer rock, fractures tend to open up a little bit more, so it's a little bit easier for them to open. But again, this is also combined with low toughness, and low toughness wants to make skinnier fractures. So yeah. But again, in our simulations, from what we know, typically propan allows to enter the horizontal fractures. And a follow-up to this, I know maybe somebody is going to ask, it's about what is the propan transport mechanism in horizontal fractures, because it's going to be very different, right? So the propan transport mechanism, must be very different in horizontal fractures because your grains kind of roll on the surface instead of they kind of flow with fluid. And so far we don't have a rigorous model for it. We have just kind of like an edge factor saying, hey, how much slower would propan be transported relative to your normal vertical fracture. But propan transport in horizontal fractures, I think it's one of the areas that needs to be further investigated.
Okay, awesome. Santiago has 2 questions. The first is, you've emphasized the role of stress in this. What is the role of fracture toughness in a combined scenario? And then secondly, you've shown some field examples. Are there and some simulations? Are there any laboratory experiments that support this?
Okay. For toughness and stresses, and so let me just put it all a little bit together, and also tensile strength. So tensile strength and anisotropy affects initiation. Okay, and so it helps to initiate horizontal fracture, not to propagate, to initiate. So if you have low vertical tensile strength, so it's easier to initiate. Then for fractures to take fluid is a stress contrast. So once you initiate it, now stress anisotropy becomes important because, like in this scenario, right? So we have both vertical and horizontal fractures. Now, even if you initiate a horizontal fracture, but due to low tensile strength, but vertical stress is still quite a bit higher than horizontal stress, all your fluid from horizontal fractures would be, compressed and flown into vertical fractures, and vice versa, right? And so in order for fractures to propagate, this is stress contrast basically. It has to be nearly isotropic, and toughness determines, how easy is for horizontal fracture to propagate, right? So how easy? So basically, the final size. So the tensile strength is initiation. Stress is your kind of general propagation or fluid balance between vertical and horizontal. And fracture toughness is going to be the actual size of horizontal fracture. So the lower toughness, the larger the size. And the second question was about lab experiments, right? Um, so I mean, there are some lab experiments. I mean, I think we had a presentation by Andreas Michael, right, from the University of North Dakota. Here, he gave a seminar, I think, a few months ago. So he did a lab experiment in gelatin, where he did. So basically, I think it was mostly isotropic to begin with, and so you have your first fracture would be like vertical, and then because it creates a shadow, your second neighboring fracture would be horizontal. So essentially, kind of you can see this how this flipping of state of stress affects fracture geometry. So there are some lab experiments, but I wish we could have more, as usual.
Andreas, you mentioned his name. His question tends to be next, and he's wondering if you could re-summarize some of the methods that you listed for mitigation.
So for mitigation, again, so as I said, it's rock plus operations. So you first need to understand your rock a little bit more. Maybe you have spend more effort on finding the stresses, stress contrasts, right? Maybe like locating all these weak interfaces and so on. And then as soon as you understand this a little bit more, it's operations, right? Um, and from operations, so basically, your biggest parameter is your fluid intensity, right? Fluid loading. So how much of volume of fluid you pump per volume of rock, right? And so basically, if you reduce it, you have less horizontal fractures. If you increase it, you have higher chance of horizontal fracture. And this is again volume per volume. So you could change cluster spacing, or you can change well spacing again, because all these parameters affect, again, it's volume per volume, or you can reduce injection rate, right? Or you can reduce injection volume. But again, if you go from 6 clusters of design to 10 clusters of design with the same fluid loading, it's not going to affect the result much. So.
And so Greg has two questions. One you can answer as a technologist. The second you're going to have to answer as a policymaker. The first question is, do you have examples where you've compared your simulations to actual field data? And I presume that's the case.
This is coming. So we just submitted an abstract to HFTC for next year. So we have a specific client project in Canada, and so we have casing deformation data, and so we developed a calibrated model to these observations. Yes, so it is coming, and we'll probably have more.
And the second question, and Greg, I'll try and summarize it, is do you see any implications for wastewater disposal? Because it is coming up frequently from the perspective of seismicity.
It's a good question. I mean, I think I never thought about it, but I mean, it could be because I mean, again, we need to look at the rock, right? I mean, because if the rock is fairly isotropic and so on, probably horizontal fractures will not be there. But you never know. I mean, if you inject too much for too long, maybe you can have some sort of horizontal fracture along a barrier, right, from the reservoir to shale or something.
And Merrick has a relatively extensive comment, but I think the message is that horizontal fractures are seen in Polish shales, and so
Mhm.
this is particularly true in situations where they see rapid changes in the stress regime. Uh,
Yeah.
Merrick, I apologize if I misrepresented that, but I think it's a very insightful comment.
Yeah. Well, I actually to follow up on this because for many operators, this horizontal fractures is a little bit of taboo topic, right? So that's why there is not a lot of published information about it because you know they observe something weird. I mean, they either don't have time to look into it or they basically sweep it under the rug. And especially because I gave this presentation actually 2 times in the Middle East. And especially like in their culture, I mean, everything has to be perfect, right? And so a lot of these cases are just not being reported, not being published, and so that's actually but it doesn't mean that it's not happening, and so that's why all these comments like that, I mean, are very, very valuable because in personal conversation with many people, I heard that, hey, we also observed something kind of weird behavior and we suspect horizontal fractures, but we never investigated it, or we were not allowed to investigate it. But I think as public becomes more and more aware, I think we need to make sure that we go back and actually reinvestigate all these cases because this could be important.
I can fit in two more questions. One is from Wenching, and he appreciated the talk, and he wants to know if you could speculate as to whether horizontal fracturing is one of the reasons that fracture swarms are observed.
Oh, that's the first time I got this question. Let's see. I don't know. I mean, I personally think that no. I would say no, then yes, because you see, we had observation of fracture swarms and this observation wells, right? um in whatever science pad, but we didn't see horizontal fractures in there. So I think there's at least one field evidence point that, well, again, maybe we are not looking for horizontal fractures, I don't know. um but at least if there are no horizontal fractures in that case, but there are fracture swarms, so probably this is not kind of the reason for fracture swarms. And also we had a few talks. I think we had a presentation by Alexis Savitsky a few years ago on fracture swarms. He has very different opinions. So he thinks it's more of poroelastic stresses that cause it. So basically, it's more like when you drop down the pressure rapidly, um, then you can have local situations when you essentially pore pressure exceeds minimum horizontal stress, and then suddenly you can have the swarms. But again, we can speculate about it, but my initial intuition says it's probably no, then yes.
Oh, no, then yes. Okay. Uh, so the final question we'll give to Wei Fu. And his question is, in the accumulated stress shadowing analysis, did you consider fracture closure after pumping, or did you assume the fractures remain fully open?
Yeah, I assume fractions are fully open because it's very simple estimate, right? So and again, if you go back to this analysis, I mean, what is important is only like few neighboring stages, maybe two, three, four, and so the time difference, because right now everything is super fast, so the time difference for these four stages is probably just several hours. I mean, it's not negligible, so there could be some fracture closure, but in shell, as far as I remember, the typical fracture closures, is about, maybe 20, 24 hours or something like this. So we should be okay. But yeah, I mean, fracture closure definitely will reduce this estimate, that's for sure. But again, it will actually change it because what happens is that because once you leak off, now you start having pore elastic effects, right? You see, because then you increase pore pressure in the rock, and this also causes swelling and some stress shadow. It's probably going to be reduced. It's going to be less than from equivalence to shadow of an open fracture, but it's not going to go away completely, at least. So, but
And
yeah, I mean, long story short, I didn't consider it because I wanted to have the simplest estimate possible, so that just one simplest equation which can tell us which parameters affect stress shadow.
and and then I'm afraid we have to wrap it up, even though there are some additional questions, and the additional questions relate Egor, people are anxious to see your HFTC paper where you're comparing it to field data, and some people are hopefully comparing to laboratory data. And for those people who want to review this again, this has been recorded and it will be uploaded to the ARMA Hydraulic Fracturing Technical Community's YouTube website in a couple of days. So thank you all. And in particular, thank you, Egor. Just an outstanding and insightful presentation.
Thank you all.
Thank you, everybody.
Thank you, Igor.
Hey, Christine. Yeah, thanks for coming.